Continuing on page 16, let's look at section 3.5. What is that? Different ways of doing the chain rule. Now, the different ways are not different, really. We just go by the same principle. For example, look at case 1, where you have a function of 3 variables, right? And then each variable is a function of 2 variables. So how are we going to go about that? Well, then we will say to do the partial of the function with one of the final variables. We go to each original variable and then multiply by each one, getting the second variable. Okay, and that is true for case 1 or case 2 or case 3. The cases don't really make that much difference. Case 3, as you notice, that there is only a full derivative that is not partial anymore. It says du by dt. That's because the parameterization there is only with t. So everything got forced into a t, and then as a result, you only get one full derivative, but the principle stays the same. You go to each variable, okay, and then take the partial and multiply by that variable, taking derivative with respect to the final independent variable. So having said that, please do example E and F by yourself. Example F has actually another layer, so it has 3 layers. That look at this, okay? That is, the function F is in terms of x, y. Then x and y is in terms of g and h. But then g and h has its own variables. Okay, because it has R and T, R and S themselves also has a last variable. So when you need to take the derivative of all that, then what you do is peel the onion all the way to the end. Okay, apply the chain rule all the way until you get to T. And so if you work on it, then it will become evident very quickly. So that is that. And then next, let's look at section 3.6, differentiable functions. Now, differentiable functions are different from the class C1, because C1 talk about partial derivatives all continuous. So it's not just differentiable. There's also a requirement of continuity there. Whereas just differentiable, it just means some kind of differentiable as some point, but not necessarily the derivative itself is not necessarily continuous. So it's less of a requirement than, generally speaking, intuitively speaking, less of a requirement than C1. So that's why your book says that it's lying between C and C1. So it's continuous and is differentiable, but the derivatives might not be continuous. The exact definition of differentiability will be given on the top of page 17. Let's look at it. Number 5. Okay, number 5 says that now f of xy is differentiable if first the partial derivatives exist. At the AB that we're talking about. It's differentiable at AB if first the partial derivatives exist. And now we didn't say anything about being differentiable, mind you. Being continuous, only that the partial derivatives exist. Okay, and then there's this interesting formula that it has to satisfy. Okay, let's look at the formula for a second. Where it let's see, where's my formula? Right, see the formula on top here. We have so we have this thing where so the difference, okay, f of a plus delta x and b plus delta y minus fab. So the difference is going to be f1, okay, the first partial derivative, and times delta x, and f2 times delta y, and then plus some kind of an error. Okay, that's what this same thing is, I believe, is taught in calculus, I don't know, 2, 3. But anyway, but there's an error later. okay? And the error will be defined as some function multiplied by delta x and some other function called, one of them is called, the first one is pronounced phi, and the second one is pronounced psi. Now, isn't that cute? That it keeps you on your toes so that you don't get confused. But anyway, these two functions, but they perform similar similar purposes. That is, the first one multiplied by delta x and the second one multiplied by delta y, and in such a way that both those things go to 0 as the delta x and delta y go to 0. So the error is going to 0. And if this is the case, then we will call this function differentiable. And remember, differentiable only means is like the first dimension is only differentiable. It doesn't mean the derivative is continuous necessarily. So it's a bare minimum requirement, okay, for differentiability. So as a result, let's look at some kind of that if you stare at that equation, you realize that the phi and the psi, those two funny-looking Greek things, they have to themselves become 0 as delta x, delta y go to 0, and they have to they are also being multiplied by delta x and delta y, which means that when you take when you divide delta and x and delta y out of it, this equation still goes to 0 as the delta x and delta y go to 0. Okay, so that's why it's similar to the first dimensional concept. Now let's to see how this might work, let's look at an example on the following example, where it says fxy equal to 2 minus y plus 2x squared minus x squared y. Some made up sample that we just pulled off. And then, this function, of course, from previous calculus, we know that it's differentiable at every point. In particular, let's look at 0. At 0, 0, f is equal to 2, f1 equal to 0, f2 equal to minus 1. Now, please work that out. Okay, let me show you. Now, take a look at what I have here. And you see, I have the whole thing written out. First, I recopy the theorem here, okay? This is important for you to do, to write the whole thing out, especially if the theorem is long and slightly convoluted, right? So then, so I wrote the whole thing out to confirm to myself what we're talking about. And then next, once I wrote that out, then I did exactly what the book said. Here's the function, okay? I calculated f1 to confirm that the book is correct, where at 0, 0, it does equal to 0, and f2, I calculated f2. Remember what f1 and f2 are, that they're the partial derivative with respect to first precision variable or the second precision variable. And that's how the book likes to call it. So the f2 then take derivative, that is f1 is partial with respect to x, f2 is partial with respect to y. And then we're continuing, then we have, I write this whole thing out, okay? So f equals a plus delta x, etc. I actually plug this in where a and b are 0, right? And you plug in the delta x and then come up with a whole pack of stuff if you plug everything into this formula. And so I come up with these things, and then eventually I came up with this thing. Now, once I have this, we can make up what phi and psi has to be. And there's more than one way, right? For example, we can pick this way, as your book shows, or we can pick this way. And all we need is that phi and psi are functions of delta x and delta y such that it goes to 0 as delta x, delta y go to 0. So that's all we need. And that's how your book came up with what it did. So please do this yourself, okay? Very important, so that it's this whole thing is clear in your own mind and not just be reading the book, not just watching the book do it, but actually go through yourself. It's like the coach shows you how to throw the ball across the field, and once you've seen him do that, then, throw the thing over yourself. Not that I've ever done that. Now, to prove that C1 implies differentiable, what we're going to do is pull this trick. Okay, here's a neat little trick. Where's my trick? Here it is, over here. All right, so we are going to let phi and psi equal to those things. Okay, And we're not just doing this for no reason. We're following Theorem 3 on page 13. And then when you do this, but before we look at Theorem 3, look at this thing. Okay, what does this mean? If phi and psi are defined that way, that means as delta x and delta y go to 0, phi and psi will both go to 0. Why? Because phi and psi are defined by f1 and f2, and being that f of x, y is in C1, f of xy is continuous. Right? So then, which means continuity means that phi and psi will go to 0 as the values go to 0. Okay? And so there's no surprises there. And at this point, we're going to substitute in. So, but before that, we're going to look at Theorem 3, page 13, which I copied down here. And I will ask you to do the same. Okay, let's do this thing. I wrote down all this stuff, right? And remember, note that phi and psi does go to 0 as delta x and delta y go to 0 because f1 and f2 are continuous. So, no surprises. So then Theorem 3, page 13 then says that delta f is given, what is this, the mean value theorem or something? Anyway, so delta f is given like this, right? We have that f equals to theta 1 delta x and then theta 2 and that sort of thing. All right, that's what we did a couple pages ago. So then eventually, we're going to plug this phi and psi into this delta f, okay? Right into right into something. Let's see, where is it? Right, so then what is f1? Then f1 is equal to phi plus f1 plus f1ab, right? If you so we'll plug f1 out of this. So phi plus f1ab will be equal to f1 this thing. Okay, so we'll plug it in right here, write down delta x, the same way with psi on the other end, and then we that would be equal to, if we collect terms a little bit, that's exactly this thing. It's f1 and f2 and psi and phi. Now what is that? That's exactly the equation that we saw earlier. The definition of differentiability. Where'd it go? Over here. See, that's exactly this equation. Yeah, the definition of differentiability, assuming that phi and psi does go to 0 as delta x and delta y go to 0, which it does, right? We just established it in the beginning right here, and that's how this part is proven. And so therefore, f is differentiable if it belongs to C1. That is, it has continuous partial derivatives of all order. So that is so. Please do this part yourself. Similar to the way I did, so that you work this out from your own point of view. So next, in example G, we see the f of x equal to the absolute value of x multiplied by something, which is of course continuous, but it's not differentiable at 0 because there's the absolute value of x. So there's that fold there. Okay, the absolute value has, this is in 3D, but the situation is going to be the same. There will be that thing right there. Okay, there's nothing you can do about it. So there's a corner, and therefore it's not differentiable at that point. So f1, as a result, is not differentiable for one thing, and plus f1, well, for one thing, f1 doesn't exist, okay, because due to the sharp point. Now, and so please go through that yourself. Now, example H, we have an interesting situation where f of xy equal to x when the absolute value of y is less than absolute value of x, and then it equals to negative x when the other way is true about the absolute values of y and x. Now, so as a result, f1 at 0, 0 equals to 1. Now, I was wondering at first, why would that be the case? And until I realized that the graph of the domain of this thing, this business about y, absolute value of y less than absolute value of x, actually means that this area and this area are defined as x, okay, where fxy equal to x. Both of them, both here and here. Right? And then up here and down here, then the values are negative x. So as a result, the derivative in this direction does exist and is equal to 1. okay, because it's equal to x, so the partial derivative equals to 1. Whereas, and then partial y, of course, there's no y here, so the partial y is naturally 0, always. Now the point, however, is just because the partials exist doesn't even mean that this thing's differentiable at 0. And the reason is that, the reason is we can plug something in and see something weird comes out. And let me show you. That is, if it were differentiable, then this particular formula earlier from the page would apply, right? Okay, so this formula right here, and on the same page and in above, where we plug this thing in, where what is that? F of right. We plug this in and establish this equation, and if we did plug it in, then we come up with this stuff. Okay, and then eventually we get, as phi and psi goes to 0, this thing has to be 2, which is not going to happen, because if it were which means it's not differentiable, because if it's differentiable, it's supposed to go to 0, not 2. And therefore, we have a contradiction, and as a result, this function f is not differentiable at 0. So please do that yourself as well. And the next one we need to do is, I should say that means that if a function is, there's a point to this. What is the point? The point is, for example h, is that just because a function is continuous and doesn't mean that it's differentiable, I guess. Yeah, I think so. No. That was the example g. What is the point of this again? I think the point of this is, even if the partials exist at a certain point, the function still might not be differentiable. I think that was the point. But it is continuous. Okay. So next, let's look at example I, which is a repeat of example E in section 2, which is on page 8. So please look at this yourself. This is the same as that example, except the things are being spun around like that volume of revolution thing, in 3D. And if you don't know what I'm talking about, just plot this thing out in the Desmos calculator, or just imagine it. Okay, if you stare at it long enough, then you know what I mean. So being that it's a repeat of the previous example, I'm not going to go over it in detail, but please look at this carefully yourself to make sure that you understand what they're saying. What they're saying is that that previous example works the same way, is that while it is possible to calculate the derivative at the point 0, because the thing was so wrinkly and so jiggly and all that stuff, it actually the function is actually not going to be, the differentiability is not continuous. I guess that's the point. So, and so on, because the derivative of some point doesn't even exist. Okay, so, all right, so that's that. So please look at go through example I yourself. And let's move on to page 18 on the next page, where we have a summary of all the stuff that we have learned, which is a bit of a list, okay? So we'll summarize it here so that we can look it up if necessary. So the summary says first that C1 implies differentiability, because differentiability, C1 means continuously. The derivatives are continuous, whereas differentiable just means is there, it exists. Okay, it might or might not be continuous. So C1 implies differentiability, which we proved a little bit earlier. In the previous page. Next, if f is differentiable, that means f is continuous. That we haven't proved yet, but we will be doing that in homework exercise number 17. And part 3, there exist continuous functions not differentiable. So, that is fairly obvious, right? And that shows up in example G, where we have that sharp point situation of the absolute value. And then next, line 4, there exist non-differentiable functions that have partial derivatives. Maybe that's what it was trying to say. Anyway, so that was example H, which we did a little bit earlier. And then finally, there exist differentiable functions that does not belong to C1. That's the last example I that I asked you to look at more carefully yourself. These are just different situations that where differentiability, which way it implies, and partial derivatives, how that works, that sort of thing. A pack of details that are somewhat interesting, okay, so that we can look at it and have a solid understanding of how the differentiability works in special occasions. So with that, we have come to the end of section 3. So for homework, please do, let me get the homework. So for homework of this section, please look at, please do problems on page 18, number 1, 4, 10, 11, 14, 16, 17, and 18. And that is also written down under the video description. And when you are finished, and then I want to talk about some, well, all of the problems. So now that you are finished, let's look at some of the homework. Now the number 1, that is pretty standard. We have is basically the same stuff we did in Calculus 1, right? And we're doing it, of course, following Theorem 4, the chain rule, which is on page 15. I have it all written down here. So here's the problem, and here's the theorem I'm following. Please do a similar thing like me and write down which theorem, which page that you're doing this from. Okay, that way you keep your mind clear. So we follow the Theorem 4 and crank something out by taking partial derivatives and came up with the right answer. And then, but there's a faster way of doing it. We can simply plug x and y into u, okay? And if you did that, it happens to be a very simple answer, and then so partial u, partial r is easier to come up with. But either way, we come up with it, okay? And that is the end of problem 1. And then problem 4, we are following, problem 4 is we're following Theorem 3 on page 13. And it's identical to example C on page 14. So please write that down as what you do is you follow example C on page 14. Okay, so we write this stuff out. What is that? The mean, law of the mean or something? Yeah. And then you notice that delta x and delta y are given, but we are not going to use it in this example because it ends up being canceled out. So we have f of x, y, and a and b as 0, 0. We plug it into the well, we first have to calculate what f1, that is partial with respect to x, and f2 partial with respect to y, what these things are, right? Once you calculate it, then you plug it all into this thing. Yeah, you plug it all the way in and you come up with this equation, this one and this one. And then we are going to line them up. That is, we're going to say that the delta x stuff, we'll line them up together to calculate theta 1. And then delta y stuff will be lined up to be equal to theta 2. There's still a 3 delta x, delta y in there, but they're on both sides of the equation, so we're going to ignore it, okay? It cancels out. And as a result, we come up with theta 1 and theta 2 both equal to 1/2, and that is the right answer. Next, let's look at problem 10 and problem 11. That is a similar situation. Well, no, I mean, that's just the chain rule, okay? From calculus something, that when we back when we did the chain rule. So you will apply the chain rule, and then we'll get the right answer fairly quickly, okay? There's several zeros here, so then you can ignore the zeros, but generally speaking, it follows the chain rule nicely. At the same as problem 11, okay? Just follow the chain rule very carefully, and then we'll come up with the stuff. And then you eventually will realize that this thing equals to this equal to that because, well, for one thing, this part, when you add up this plus that, okay, sine and cosine becomes 1. This plus that is, this cancel out with that. They are the identical thing, but subtracting. And similarly, this plus that is the second one, so everything works out. Now, how did the partial derivatives with two kinds of variables equal? The reason they're equal is because the partial derivatives are evaluated at the other one, see, at our theta. And you have to plug in this equation, you have to plug in x equal to r cosine theta and y equal to r sine theta. That's why everything works out like it's supposed to. Next, let's look at problem 14, where we're supposed to do some quick limit calculation. So, and problem 14, we have once substituting things that up there and down here, we have a 0 over 0 situation in the L'Hopital's rule. So we apply it. Please look up the L'Hopital's rule if you don't remember what it is. Okay, it's a very easy to apply rule. And so once we apply it by taking derivative of top and bottom, then we end up some kind of value. A equals to 1/2 once you get through all the fractions. So that's that. Now, problem 16, we have a very interesting situation where the function f is 1 or 0, and that is the function f is 1 except along the x and y axis where it drops down to 0. But only along the two axes on the ground, which means you can't see it. Okay, it means is the hole that is the hole it has is the width of a line, and the line has no width, so you can't see it. But it sinks down right along the right along the x and y axis, where it sits on the x and y axis. It equals to 0 along those two things. That's what x, y not equal to 0 and x, y equal to 0 means. So then what? Then what we have is what happens at 0 then? What is the limit? Well, then the limit at 0, it will go to either 1 or 0 depending on how you get there. So as a result, the limit doesn't exist at 0. And well, the thing isn't even continuous, right? However, the double limits as you approach it, however, does exist because and the double limits exist and equals to 1. Okay, because if x and y, because the double limits are calculated when x and y are not 0, and as a result, then the double limits exist as being 1, and you can see that. And this is similar to example B on page 12. So here's another interesting phenomenon, where the limit might exist and equal to 1, and yet the function is not continuous. It's just one of those cute little exceptions that we'll look at and probably forget later. Now, so let's look at the next problem, where we say that differentiability implies continuity. Now, that is a easy problem to do because, as always, differentiability is the much stronger requirement. Continuity is nothing in comparison. So the implication is theoretically easy to do. Now, in practice, a book even gave us a hint. Okay, we'll just write down this thing, being that it's differentiable, this works, and then automatically, since these things go to 0, then the limit then will be 0, which means f of x, y does approach f a b, and by definition of continuity, which is on page 12, okay, and then this thing, differentiability, does prove continuity. So that would be that. And then one more problem, which is on page, page 8, problem number 18, where we have this function, and we have to show that it is differentiable at 0, 0. But what? Well, we have to show that this thing is differentiable, okay? Okay. Now, problem 18, we are supposed to prove that this function is differentiable, okay? And the function, it looks decent except at the origin. That's the only place that it might have a problem. And, well, it's the only place that it cannot be defined unless we come right out and define it, and we'll define it as 0. Where we're at the origin. So together, as you can see, the function does approach 0 at the origin, and as a result, it is continuous once we define it as 0. The question is it differentiable at 0? And that's what we're going to explore. And to do that, of course, first we got to take the partial derivatives, okay, before we do anything else. So here's the partial derivatives, which are slightly annoying to do. Okay, there's a lot of stuff, but eventually you get somewhere, something like this. And once we have that, then, and the next question is, but the derivatives are not defined as 0 either, right? So what we're going to do is then define the derivatives to be 0. That's because differentiability means the partial derivatives has to exist. And And so we'll make it exist by defining it as 0, which is fine, but does that make sense, however? So you can calculate the limits of these fractions and prove that it does go to 0. I was too tired to bother with doing that, okay? The fractions and stuff. So I just plotted it out. I mean, take a look at it. This is f1. Okay, partial f partial x. As you can see, it is everything goes to 0. It's all wrinkly and stuff, but it does go to 0. And therefore the defining f1 at 0 to be 0, it does make sense and similar to as to f2. So as a result, the partial derivatives are also continuous, which means the function f belongs to C1, continuous first derivatives. And if it's anything that is in C1 is differentiable, right? We have a rule that says that. I think it was rule I on page 18, I guess. I have it written down here, so I assume that's correct. And so then that concludes our proof, actually, that the function is differentiable if it belongs to C1. So and that concludes this section.